Hi everyone, it's Dr. Marks, and our topic for today is what is statistics and why do we care about it? So let's get started. Well, first of all, I want to make sure you understand what we're going to do in this lesson, and we're just going to introduce the idea of statistics. Now, we're going to focus on the general definition of statistics, and we're going to come back to that many times because as you're going to see, it's got multiple parts. Specifically, we need to think about descriptive versus inferential statistics. Now, we're going to cover this in significant depth throughout the semester, but it's important as we go into the class that we understand the distinction. I'm also going to introduce some terminology, and we're going to be expanding upon this terminology in future lessons. We want to think about cool ways statistics has been used in the real world because statistics and data is all around us. So let's start by looking at some interesting statistics, and I just found some great examples. And you're going to see that these statistics include numerical facts and figures, and they're connected to the idea of data. So I found some data that says the United States is the third most visited country by international tourists after Spain and France. Now, they didn't give me a specific date, but the data was reported in early 2020. So I'm guessing that this is probably data from something like 2019. Or in 2020, the United States was home to nearly 45 million immigrants, and this was more than in any other country in the world. Interesting. Now, we rely on statistics because we make decisions in our own lives based on statistics and the data. So, for example, a great one, birth control pills are considered to be 99% effective in preventing unwanted pregnancies per the Cleveland Clinic. Now, how many of us have relied on that particular statistic in decision making? Certainly a lot of us who wanted to delay having birth. Second, based on evidence from clinical trials in people 16 years and older, the Pfizer-BioNTech vaccine was 95% effective at preventing laboratory-confirmed infection. All right, so here we're talking about making decisions about should I get a certain vaccination? And the CDC says, hey, you should, it's highly effective. IRS statistics from 2019 show that individuals with incomes between $200,000 and $1 million had up to a 1% audit rate. Seems really, really low. So what would that signal to you? Well, if you're super high income and you want to cheat on your taxes, the probability of getting audited is definitely very low. All right, you get the idea. But one thing I want you to understand is that the interpretation of statistics is also important. And so that's one thing that we want to be thinking about. Are we translating this information correctly? For example, a study finds that women professors at a large public university make an average of 75% of the salaries of their male counterparts when we control for experience. So we see these kinds of studies a lot that make these large sweeping claims. All right, clearly this type of statistic might be used for women, to say, look, we're being discriminated against. And okay, it could be true. But here's the thing. We have to take a much closer look at this. We can't just jump off from this particular claim and say, oh, women are discriminated against. This is so unfair. We have to do our jobs. Now, we've already said that in this example, we are controlling for experience. So that would be the first thing to think about. Well, look, are we lumping all women together and comparing them to men? What if women have less experience than men? Okay, but we've controlled for experience. So when we control for experience, people that each have 10 years of experience, 11 years, 12 years, etc., this is what we find. But we need to ask ourselves an additional question, and that is, are there things other than gender that might explain this? So can you think about other things that might give us the result that women are paid less than men? Well, what if males at universities dominate engineering and medical schools? I'm just saying, what if? Is it possible that engineering and medical positions pay higher? Sure. And what if women dominate fields like education, which tend to be lower paying? If that's the case, could we get a result where women make less than men without there being discrimination? We certainly could. Now, don't get me wrong, not trying to say women aren't discriminated against. I'm saying as an economist and a data person, before I jump in and say, oh my gosh, we have a problem, I need to do my research. I need to make sure that the conclusion is sound. And my guess is I can dismantle some of this when I think about things like this. One other thing that we find is that women might have more work interruptions. Perhaps women enter and exit the labor force, and they might have the same number of years experience, but maybe it's been broken into chunks. Why would a woman enter and then exit the labor force? Well, maybe to raise children. So I might have 20 years of experience, and somebody else, my male counterpart, might have 20 years of experience, but maybe mine really spans 30 years because I took time off to raise children. And that could have wage impacts in the labor market. All right, you get the idea. Here's another study. This study showed that there was a large correlation between crime and police expenditures, leading the study to conclude that more police leads to more crime. Now, hopefully you're scratching your head. Okay, we have a large correlation between crime and police, leading to the conclusion that more police leads to crime. We hire more police and we're going to end up with more crime. Well, that just doesn't seem very logical, right? So the first thing we need to realize, and we'll be talking more about this, is that correlation just means two things move together. It doesn't imply causality, right? Causality means one causes the other. So we're going to be expanding on these kinds of topics, but this is the kind of data illiteracy we see a lot, where people confuse correlation and causality. In addition, if we do think there's a causal relationship, couldn't it actually go in the opposite direction? So what would it mean if the causality was backwards of what's suggested? Well, it would mean that more crime means we need more police. So if we have crime and police being correlated, it's possible it's because there is a causal relationship, but it's not police causing crime to go up. It's that when we have more crime, we need more police. So again, we have to dive in and make sure we are being articulate and doing due diligence to explain things correctly. Now, here's another study that found areas with more churches have more crime. So areas with more churches have more crime. Does that seem like a legitimate conclusion? Well, you're getting the hang of it. What might we need to think about here to decide if this makes any sense at all? Well, is there a causal story? So maybe there's just a correlation, but is there a causal story? So we build more churches and we're going to have more crime. That seems really backwards, right? But here's the thing. Cities have more churches, right? And cities generally have more crime. So what should this lead me to believe? That probably this relationship's not explained by churches at all. What explains the connection between churches and crimes? Well, it's explained by a third variable, and that's cities. So again, this would be an accurate conclusion made by somebody who's not doing a very good job working with data. So let's dive into the definition of statistics. When we think about the definition, we often see this particular one. So this is going to be our formal definition: the science of collecting, describing, and interpreting data. The science of collecting, describing, and interpreting data. So when we think about this definition, we're going to clearly explore these three elements: data collection, descriptive statistics and visualization, that's the describing part, and then making inferences and doing statistical tests, that's the interpreting part. So collecting, that's our data collection part. Describing, that's going to be descriptive statistics and visualizing through well-constructed graphs. And then interpreting data, making inferences and doing statistical tests, like, for example, hypothesis testing. Now, when we think of statistics, we often divide it into two areas, as suggested by that definition we just went over. We've got descriptive statistics, and when we think about descriptive statistics, we're talking about things like the collection, presentation, and description of sampled data. So I have a data set, and I'm going to present information about it. I'm going to describe it. But then we have our second area, and that's our inferential statistics. And that's going to be where we make decisions and we draw conclusions about a population. Remember, we have a sample of data, and we're going to use that sample to make statistically sound conclusions. So we have descriptive statistics, which is aptly named, right? We're just describing the data, and inferential statistics, where we are inferring things from our sample about our population. So a little more on descriptive statistics. Again, the collection, presentation, and description of sampled data. So we might summarize data in meaningful ways. And when I work with a data set and I'm writing up a report, summarizing my data is probably where I'm going to start. But I might also be looking for some interesting patterns. But beyond summarizing and looking for patterns, and that could involve also creating graphs, keep in mind, the last bullet's important. We cannot make conclusions beyond the data. Descriptive statistics are just what they are. We can't make inferences from our descriptive statistics. We just use them to highlight what the data tells us. But inferential statistics, as we said, that's where we're going to make decisions and draw conclusions about our population, again, from our sample. Now, remember, populations can be really large. If I'm looking at, all professors in the United States, that's a very large population. And I'm not going to be able to get data on all professors, so I need to get a sample. So maybe I survey 500 or 1,000 professors. I've got a sample that hopefully reflects my population. And so what I'm going to do is use those samples to make generalizations about the population. And so our inferential statistics allows us to make conclusions. So if I were to ask you, do descriptive statistics allow us to make conclusions? No. Do inferential statistics allow us to make conclusions? Yes. So descriptive statistics are some things you've already heard of. For example, measures of central tendencies and measures of location. Those are some really fancy words for things we already understand. Mean, median, and mode. Those are measures of central tendencies and measures of location. And we're going to be going through these, even though we all probably already know what these are. But those are descriptive statistics. Then we've got what we call our measures of dispersion. Things like standard deviation and variance. And I know you've heard of those terms as well, so we'll be going through those. But these are purely descriptive measures. And then we're going to cover some data visualization. And that's going to be things like graphical constructs. Pie charts would be a really simple example. Frequency distributions, a more sophisticated example. And some of you have a background in this, and you've probably done tons of great data visualization. But I want you to understand that these three things simply describe data. I cannot make inferences from these things. I can't make conclusions. I can't generalize from my sample to my population. And hence, that's why we call them descriptive statistics. But when we're talking about inferential statistics, again, we're making decisions and drawing conclusions about the population. From where are we drawing these conclusions? From our sample. So we have to do some sampling. We need to get data on a subset of our subjects in order to learn about the population, right? If there are thousands of professors in the world, I can't sample them all. I need to get a subset. So sampling is going to be key if I want to be doing any kind of inferential work. And then we can use some hypothesis testing. And hypothesis testing, we're going to be finding evidence for or against a theory. And so I know everyone's probably done some hypothesis testing, trying to decide if your null hypothesis makes any sense. So remember language like we reject or fail to reject the null hypothesis. I know it's coming back to you. For some of you, I know it's been many, many years, but don't worry, we're going to be going through hypothesis testing as well. So clearly, we need to talk about data collection in this class because we're starting with a population of interest. So let's say we're starting off with the idea that we want to investigate salaries of newly minted CPAs in the United States. And I want to collect data on their beginning salaries. And that's my population, all newly minted CPAs in the United States. But we agree that this is a very large data collection process, and I can't possibly collect data on everyone. So instead, we're going to collect a sample. And maybe my sample is I'm going to look at 2,000 newly minted CPAs. And so I have a good size sample. Hopefully I've collected it well, and I can make inferences about my population. Now, we can learn a lot from descriptive statistics and the visualizations of our data, as we've just explained. And when we think about descriptive statistics, there are no uncertainties about the values we get, right? So let's say we collect the starting salaries of all Longwood Business School graduates, so all of our undergrads, we collect all of their starting salaries, and we calculate the mean, and we all agree that the mean is the mean. There's no distribution. The mean is just a number with certainty, and the mode is the mode with certainty. But I can only make summations about the subjects I have data for, and maybe I don't have data for absolutely everyone. And so I can't infer to the larger population. So maybe I can collect data on Longwood business students who graduate, but that doesn't really tell me about business students in general in the United States who graduate. I need to be able to infer. So in this example, I don't know that this is what graduates from other universities are earning. I just have this sample of Longwood students. And I don't really know if what I learn about Longwood business majors is going to extend to all of those graduates from all those other universities that have business majors as well. So descriptive statistics don't let us infer about the population. If I know the mean Longwood student salary and the median Longwood student salary, that's great and that's useful. But those descriptive statistics don't let me infer anything about business majors in general across the United States. And so for that, we need the inferential statistics, and that will allow me to get a better sense of how well does my sample represent the population. So inferential statistics is the mathematical procedures whereby we convert information about the sample into intelligent guesses about the population. Let's look at that again. Inferential statistics is the mathematical procedures whereby we convert information about our sample into intelligent guesses about the population. So, hence the name inferential. We're trying to infer from our sample to the population. And it's the inferential statistics that allows us to generalize from our subset to our population, right? From our sample to our population. But here's the deal, folks. Our ability to infer in this way depends on our samples, right? Does our sample reflect the population? When we're sampling, hopefully, we're getting a sample that does reflect the population. Or there could be selection bias, right? What if I collect my sample in a way that's not representative of the population? What if I collect it in a way that leads me to really inaccurate conclusions? Well, then I have selection bias issues, a topic we'll talk more about. So to get good information about my population, I need good sampling techniques. And when we think about good sampling techniques, we're talking about techniques that result in samples that reflect the population. So as I sample, I have to think about if my manner of sampling, if my method of sampling is going to give me a subset that reflects the population. Now, one way to do this is random samples, right? I could take a random sample, and if I do that, then hopefully I'm going to end up without any kind of skewness or bias that would distort my sample. But I also need a sample of sufficient size, right? So I need an unbiased sample of sufficient size. So for example, what if all of my data about new CPAs comes from Harvard, Yale, and Princeton? So I was like, okay, I've got friends at Harvard and Yale and Princeton. I'm just going to have those guys sample their students who just got CPA licenses, and we'll get the data that way. Well, I know you obviously understand this is going to create some bias. Can I successfully extrapolate from this sample of like really, really high achieving students from, some of the best universities in the country, maybe in the world? Can I successfully extrapolate from that group to the population of interest, which is all CPAs in general? Well, probably not. And what if I only collect 15 observations, right? Because how many times have you seen a report that's based on really, really small amounts of data? Well, even if I collect randomly, if I only collect 15 observations, isn't there some reasonable probability that just by chance I collect a set of observations that isn't representative of the population? Certainly could be the case, right? Now, continuing on in our discussion of statistics, some of you might be involved in research that's experimental. I can imagine that a number of you are in industries where your mode of inquiry is experimental. And so when we think about experimental research, we're talking about where our goal is to use an experimental design to test the effect of a treatment. So you've got some kind of treatment in mind, and you have to set up the experiment. And so when you guys took undergraduate statistics, I know you talked a little bit about experimental design and treatments. So here's an example. Is productivity similar when your employees are allowed to work from home? Maybe this is an experiment of interest for you in your workplace. So if we give our employees the flexibility to work from home, do we end up with the same productivity? Well, I myself would love to know the answer to that. So this could be an experiment that we run. Now, to do this, we would have to randomly assign some people to work from home and others to work from the office. And notice I said randomly assigned, right? I need to be a little careful. I can't say, okay, all the accounting departments are going to work from home. Marketing department, you guys are going to work in the office, right? That's not random. So I could end up with some selection bias in my treatment design, right? So I need some random assignment. And as we talked about, I also need a big enough sample. If I just do this with 5 people, that's probably not going to be enough. So I need to randomly assign some to work from home, some to work from the office. Now, in this design, we have what we call a dependent variable. And you're going to hear the term dependent variable in some of our units. Our dependent variable is our outcome variable, the thing that we're measuring. And the thing we're trying to measure here is productivity. So when we think about what we're doing, we want to measure productivity given our different treatments. So productivity is our outcome variable, our dependent variable. But we also have an independent variable. In this case, just one. We could have multiple independent variables. Talk about that later. But our independent variable is our control variable. And our control variable here is that treatment. We're controlling the treatment. So location, work from home or not. So I really have an independent variable, work from home. All right, so we have a dependent variable, our outcome variable of productivity, and we have an independent variable, that control variable, the treatment variable that we're manipulating, location of your work. So the independent variable is manipulated in this case to see if it impacts the dependent variable. So does location affect productivity? So you need to make sure, if I were to give you a scenario, that you can identify the independent variable, the thing we're controlling or manipulating, and the dependent variable, our measure of our outcome. Now, in addition to the experimental research you might have seen, some research is non-experimental. In economics, we actually have both types. But why would we have non-experimental research? Well, because sometimes an experiment is just not possible, or maybe it's unethical. So here's a good example. What if I want to look at the impact of drinking on college students' grades? So again, do we have a dependent variable? Yes, grades, right? That's my outcome variable. Do we have an independent variable? Drinking. But here's the problem. I can't set this up as an experiment, right? Because I would have to create a drinking treatment. So I would have to, announce to my students, hey guys, I'm doing an experiment. I need some of you to sign up for this study, and you're going to be drinking really heavily during the week while you're supposed to be studying. Obviously, cannot do that. That would be unethical. So instead, I need to collect data in another way so that I can code information about behaviors. So what might I be able to do here if I want to undertake this study? Well, maybe I can do this via surveys. Now, again, we can get into later design of surveys if people answer surveys truthfully. And if I get a survey put together that people answer truthfully, then I can kind of investigate this question here. But they've got to be able to be truthful about their grades. They've got to be truthful about the amount of drinking. But you get the idea. This is non-experimental because running an experiment on the effect of drinking on college students is just not going to be allowed. But here's the thing. If I'm going to run this as a non-experimental investigation, I have to be sure that people who drink at different levels are amongst my respondents. Now, what am I saying there? Let's say I give everyone the survey and it turns out nobody drinks. I've got 500 observations and nobody drinks at all. I've got nothing to explain, right? I don't have any variation in that independent variable, that treatment variable of drinking. I'm hoping that with my 500 respondents, some don't drink, some drink lightly, some drink moderately, maybe some people are heavy drinkers, and then that would allow me to have enough of a range in that treatment variable. Now, as we've said, non-experimental research still has a dependent and independent variable. We just covered this, but let's remind ourselves, our dependent variable, our outcome variable is GPA, because I want to know how is GPA affected. So my outcome is GPA. My independent variable is the level of drinking. And as we said, I'm hoping in my data set, when I code all of this data, I have different levels of drinking because that's my treatment variable, my independent variable. But do you also agree that I might need some other control variables? If I simply look at GPA and drinking, I'm leaving out a whole lot of other potentially relevant things that I should be controlling for. For example, do I want to control for male versus female? I don't know. It's easy to do. So I probably statistically want to see if it matters. It might be that I rule it out, that the effects of drinking on GPA are not different for males and females, but a good investigation should rule that out or determine if there is an influence. But what about ability? So not everyone comes in with the same ability, and ability affects GPA, so I need to dismantle the effect of ability. Ability can be hard to measure, though. So I might have data on IQ scores, or SAT scores might not be the best measure of ability, but if I'm working with college students, it's probably the closest thing I have. But certainly there are different measures I might want to incorporate. What if people are working jobs, right? Potentially working a job could affect your GPA independent of drinking, right? And so I might want to control for how many hours a week somebody works. Doesn't mean your GPA is going to be lower, but for some it might be harder to manage their academic pursuits on top of a job, especially if they're working 25, 30 hours. And again, some of you are thinking that's probably true about this MBA class, right? That you're a little worried about working that job and getting good grades. So you understand where we're coming from. One other variable I might want to take into account is, do students live on campus? Turns out the data seems to suggest that living on campus is good for your GPA, holding all else constant. Maybe there's less distractions. Maybe you're closer to the library. Maybe you're closer to other people you can get help from. It's not clear what the influence is, but living on campus can matter. So you guys understand that we're talking about a non-experimental investigation related to the effects of drinking on GPA, and it would be unethical for us to conduct that as an experiment, but I can still collect data. I just need to think about control variables that might be relevant. So let's think about some ways that statistics affects our everyday life. So where do we see data? And where do we see these statistics that do impact our everyday lives? Well, let's think about approval of a new pharmaceutical type of medicine from the FDA. So my brother actually used to be involved in this, he used to run a lab, and there are huge studies that are involved when companies have to go through the approval process with the FDAs. And they are running clinical trials. Those clinical trials result in data. They have to do lots of statistical testing to show if there are any medicinal benefits from that pharmaceutical, how large the negative impacts are. Lots of different investigations going on, and clearly this is going to be statistical. We also know that decisions about how and where to campaign during election season, that's tied to statistics. So they look at voting patterns and they decide, okay, where should we put our effort? It doesn't make sense to put a lot of your effort into an area that you know is voting for the other party, but where are those areas where we see some either statistical anomalies over time, or maybe where there's more of a marginal impact, and so we can go in there and maybe change some minds of some voters. You're not going to make those decisions about allocating resources without doing a huge amount of data manipulation and investigation, trying to figure out exactly where the biggest bang for the buck is going to be. Am I right? What about insurance markets? So think about your life insurance. We know that not everyone is charged the same for life insurance. Not everyone is charged the same for medical insurance. Not everyone is charged the same for property insurance. And those all have to do with probability models. For example, if I'm a smoker, which I'm not, but if I'm a smoker, chances are I'm going to pay more for medical insurance and probably life insurance, because the probability of me dying young is higher, according to actuarial tables, right? Which means a higher payout for the life insurance company, and same thing with medical. The chance of me getting sick is higher, resulting in more expense to the medical insurance company. So clearly, insurance markets are totally driven by statistics. What about sampling for quality control in the production process? Well, if you are in charge of a large factory, there's got to be some kind of quality control process, and you're going to be taking samples, and you're going to look at the statistical elements of those samples that you're taking, trying to get a sense of, is this too much? Is this an outlier day? Is something going wrong with your process? Do you need to tighten your quality control procedures? So again, we'll do some examples tied to that later. Genetics. Genetics is all based on probability. What's the probability that offspring will receive some kind of genetic condition? So those researchers that deal with genetics are running all kinds of probability models, since probability drives all of this, and that again is statistics. So one interesting example I found along the way comes from Walmart. We all know Walmart. But what I learned is that before storms, Walmart diverts strawberry Pop-Tarts to affected areas. So very quickly, if they see storms coming, they send more strawberry Pop-Tarts. They take them from some areas that are not affected and send them to areas that are affected. Well, that makes total sense, right? The company has realize that there's a 7-fold increase in sales of strawberry Pop-Tarts when storms are being predicted. And again, those of us that are moms totally get that, right? First, you can eat a Pop-Tart without having to cook it, and kids love them. So when you're thinking about what kinds of provisions do you need to have on your shelves in the event that there's long-term power outages and things your kids will eat, well, that Pop-Tart certainly comes to mind. So Walmart studies this kind of data, and then they make allocation decisions and they divert certain products to different areas. And so with Hurricanes Harvey and Irma and Maria in 2017, they were preemptively diverting certain products to those affected areas. But even before this, the retailers were employing this thing called predictive technology, and they use all this sophisticated technology to decide what might be bought and when. It's super cool, and maybe some of you are in the retail industry, and this could be something that you're involved in. So again, shopper history gives Walmart the ability to have very sophisticated models. Now, another example comes from the movie Moneyball. Now, I'm not a big sports person, but if you've seen the movie Moneyball, you know what I'm talking about. This is dating me a little bit because this is back to 2011. But this was a movie about the manager of the Oakland A's, and he was drafting players based on statistical modeling. So they were doing some really cool modeling, and that was not generally how the industry worked at the time. So it was a major deviation from the traditional scouting model. Based on the sources I've read about this, this idea has really caught on, that instead of, scouting for other reasons, you literally treat a player as a set of statistics about their productivity, and you create models and you decide who's going to add value based on these statistical models. And it's being used now. So let's wrap up by talking about the goals of this course. First thing I want to make sure you understand is that you're not going to become an analyst from one basic course. And that's not really my goal, to make you an analyst. But you do need to have a foundation in this kind of work with data. You need to become, we all need to become, the whole country needs to become more data literate. And so the approach to this class is to promote this idea of data literacy. And when you're data literate, you can talk to other departments in your job. You're able to better interface with them and have meaningful conversations about what's going on. You can also think about good research design. And so we'll spend a little time talking about good research design so that you don't get caught in any of those pitfalls of bad research, because there's a lot of pitfalls for bad research, and you've probably seen examples. You can also better evaluate what you hear and see in media sources. And I know that all of us are concerned about the media now and how accurate they're being and how the media might be perceived as manipulating information. And if you think about it, if we're not data literate, we don't have the ability to see through that. So there's all kinds of reasons to be data literate. So again, thanks for viewing. If you have any questions, let me know. And other than that, I hope you have a fantastic day.